Okay, in that case, let's move on. So we covered 0, 0. These were the basics of deep learning and machine learning in general. Now we are going to go to computer vision, image classification. We're going to start with classification, and then we are going to go to large networks. What is the objective when it comes to large networks? You want to build a model as accurate as possible, regardless of the cost, regardless of the size of your model. Basically, you want to enter your model in a competition and win that competition. So let's see what is the best case scenario. If I give you enough compute, enough data, can you actually push the state of the art? So that's the idea here with large networks. Later on, we are going to go to small networks and start considering cost, maybe become more parameter efficient, data efficient, and so on. But for now, we can assume that you have a lot of data and you have a lot of compute in front of you. Can you win the competition? And actually, for a while, people couldn't do this with usual machine learning. You give them enough compute, you give them enough data, like ImageNet type of data is before learning. And people were using classical machine learning techniques, and they were stuck. They couldn't push the art by a large margin. But then deep neural networks came and managed to push the state of the art by a large margin in 2012 with the AlexNet paper. So I'm going to start with introduction to convolutions, and then I'm going to cover a second paper, a follow-up paper, and then I'm going to give you a bunch of assignments to work over the weekend and watch the videos on yourself. This is an image from ImageNet data. This is how we see it. We know that's a goldfish. And this is another image, or 1, 2, 3, 4, 5, 6, 7, 8, 9 images from MNIST. So what you can do is explore that data and write a report on that, either ImageNet or MNIST. This one is going to consume a lot of memory on your computers, but you should be fine. Now, here's my question for you. What is an image? Or actually, in the context of deep learning and machine learning, what is an image? And when I say machine learning, you're thinking of computers. How does a computer see an image?
It's a matrix of pixels can be converted into numbers.
You're close. It's a matrix of pixels, which is the correct way to think about it. And a matrix of pixels, you can think of it as a tensor. Okay, so it's a generalization of 1D arrays, 2D arrays, to become 3D arrays, 4D arrays, and etc. So it's a 3D tensor. What do I mean? It has a height, it has a width, and it has a couple of channels. For instance, this image here has 3 channels, red, green, blue. And as soon as you merge those channels together, you're gonna have different colors. So perhaps a better way to think about images, and when I say image, is not to think of an image like this, is to think about it like this. So that's an image. It has a height, it has a width, and it has C channels. And that's why it's a tensor. And that's why people are using TensorFlow, because you're flowing a bunch of tensors through a bunch of operations. So the question is on the chat. So does that make it 3 sets of 3D tensors that we process separately? I understand your 3D tensor, but I don't understand what you mean by 3 sets. No, if you want to think about it that way, that it's 3 sets of something, then that's going to be 3 sets of 2D tensors. Now you're thinking in terms of channels. This is one channel, one slice, and one slice of that is going to be in RH by W. So that's going to be a matrix, a 2D tensor. So your sentence is correct. It's 3 sets of 2D tensors, or you can think of it as a single 3D tensor. Does that answer your question? Okay, perfect. So this is an image, and this is the way that I want you to think about it. And as I said, C could be in the case of red, green, blue channels. So you have 3 dimensions here, 3 slices, 3 channels. And in the case of MNIST, that's going to be 1-dimensional. It's either black or white. How black are you? How white are you? And that's going to be C. Okay, so far so good. Now what we're going to do is ask another question. What is a pixel then? Using the same language. What was an image? It was a tensor. What is a pixel?
It's an element in the tensor.
Okay, and what is going to be an element in the tensor?
Uh,
Perfect. So yeah, you gave me the correct answer on the chat. So each pixel is a vector. So this is a pixel. It has 3 dimensions, for instance, 1, 2, 3. So each pixel is a vector in R3. So this is how you're going to think about it. Each pixel, how many pixels do you have? You have H times W pixels. Pixel I and J is a vector on its own. If you look at this image, you're not going to think about it that way, because each pixel, you think of it as some color of some sort, but there is actually a vector behind it. So you're going in the 3rd dimension in your screens. So you have red, green, blue. Now, every entry of these C channels, maybe let's pick a channel, maybe let's pick channel blue, the 2nd channel. Let's look at pixel I and J, maybe pixel 100 and pixel 200, channel being the 2nd one. It's going to be an integer. That's how things work. When you're saving an image on your computer, because you want to save space, that's going to end up being an integer. And where is this number 255 coming from? Is 2 to the power 8 is 256, and 8 is 8 bits. Each bit is a 0 or 1, so you have 2 options. It's 2 to the power 8 numbers that you can represent. But usually, when you are doing deep learning, you like to normalize your data. This could be one way that you normalize, so that all of your data fall into the interval from 0 to 1. So as soon as you divide by the maximum number that could happen, if you're at the minimum, that's going to be 0. If you're at the maximum, that's going to be 1. So your x, you can think of it as a bunch of numbers that are in 0 and 1 in that interval. So you're asking me, is x, I, j, c a pixel? No. Each pixel is a vector. What you just wrote in the chat is a scalar. It has a value. So that's not a pixel. That's one channel of your pixel. That's channel 2nd of your pixel, or channel 1st of your pixel. Basically what you wrote, if you're in the red channel, you're saying how red is my image, and then how blue is my image. Yes, xij is a pixel. This is a pixel. That's a vector. So I want in your minds to associate pixels to vectors, tensors to images. So whenever I say the word image, that's a tensor. Whenever I say the word pixel, that's a vector. Even if you only have one channel, think of it as a vector. So is everything clear? Okay, perfect. Now we're going to go ahead and collect training data. This was one example. In this case, 9 examples for MNIST. For ImageNet, you can collect 1 million of data, or even more. And then you know the corresponding ground truth, or the corresponding label. So that's your data. It's going to be a pair of an image, which is a tensor, again, and you have a label, which is an integer. For instance, this image corresponds to goldfish, and goldfish, according to your labels, is the 10th label. And you can have 1,000 type of classes when you're dealing with something like ImageNet. Now, here is my question for you. Let's say you want to guess at random. I give you an image, and at random, you're just going to report one of these numbers. What is going to be your accuracy? What is going to be the accuracy of random predictions? Let's say you're taking a test, and then you're just randomly selecting from multiple choices. The same thing here. You have 1,000 choices. You randomly report to me a number. What is going to end up being your accuracy?
1/k.
Exactly. So it's going to be 1/k. And the bigger your k, the harder is going to be the problem. For instance, for something like MNIST, that you have only 10 choices, if you guess randomly, there is 10% chance that you're correct. But for something like ImageNet, where you have 1,000 classes, it's going to be 0.1% that you're going to be correct. So you're much more less likely to succeed by giving random answers. So your model needs to work harder. Okay, so far so good. That's our training data. Now you see that I'm not worrying about test data or validation data anymore, because at this point, at this stage, you want to focus on training and writing a model, a good model. We want to come up with parameters. So what are we going to do? We are going to do feature learning next. And what is the idea of feature learning? The idea is that we don't like working with images. We don't like working with tensors. They are hard. They make our lives miserable. We know how to work with vectors because they are going to be tabular data. You can put them in a table and do maybe logistic regression on tabular data. The problem with images is that you cannot put your data in an Excel spreadsheet because of these images being tensors. Maybe if you flatten them, one idea is just flatten your input image. Then what is going to be its size? If you flatten it, it's going to be in RH. Now this times is a simple times, HWC. And for high resolution images and you have red, green, blue channels, that's going to be a huge sized vector to work with. Now, if you want to do MLP, you have a huge input vector that you're multiplying by a matrix, and that matrix is going to end up being huge. It's not going to fit on your GPU. You're going to need a lot of memory for that. So we need to be smarter about it. We want T to be smaller than H times WC. Another idea is do a global averaging over your input image. Maybe do a summation and then divide by the number of pixels that you have, which is going to be H times W, and just average all these vectors together. That's going to give you a single vector. It's in dimension 3. But what is the problem with that? We solved the problem that now D is very small. But what is the problem with it?
It can be anything averaged to the same value.
Yes, when you do averaging, you're losing a lot of information. Exactly. You wrote it on the chat. You lose a lot of information. In that case, D is very small. In one case, D was too big. In another case, D ended up being too small, and you lost a lot of information. Prior to deep learning, what people were doing, this was their task. They had an image, they wanted to end up with a vector. And that was called feature engineering. So you would do a lot of feature engineering. And to push the state of the art, you do a lot of feature engineering. Maybe look at the histogram of colors in your images, have a sliding window over your images, and create a bag of visual vectors and work with that. And then another person might come and say, no, maybe SIFT is a better way to do feature engineering. That's going to give you more informative features out of your image. Deep learning came along and said you can actually learn. You can do feature learning rather than feature engineering. Turn that into a learning problem. And let's assume this is solved. Let's say somebody gives us some good parameters, a good function. We take our image, push it through the function. It's going to give us a vector. Now you have a vector as input, an integer as the output. The vector, you can put it in an Excel spreadsheet. Now you have tabular data and you can work with simple machine learning techniques, multinomial logistic regression. This is exactly what we did last session. So the question is, how do you go from images to X, a vector? And the answer is we're going to use CNNs, convolutional neural networks. They are designed to do just that. Take an image, turn it into a vector. So the aim is to take an image as input, turn it into a vector. Let us start with one-by-one convolutions because I know you are comfortable with them the most because they are the most similar to what we did with multi-layer perceptrons. What do? You take a pixel, let's say this pixel. So that's your pixel. And what was a pixel? I need to hear an answer. It's a vector. So you have a vector. It is C dimensional. Now you want to change the dimension going from C to C prime. And how do you do that? You multiply by a matrix. And this is exactly what we did with multi-layer perceptrons. You change the dimension of your pixel. Now you have more channels, perhaps. And now you're going to end up with a pixel for the outputs. So with one-by-one convolutions, an image goes in, another image is going to come out. This is ijth pixel for another pixel, maybe I prime, j prime. You use the same weights. And this is the idea of parameter sharing. That's why convolutions are parameter efficient. We use the same parameters. It's always going to be the same W. Now let's move to a 3x3 convolutions. What are you going to do? You still need to know your pixel at the output. And a pixel at the output is a vector, perhaps in our C prime. It has C prime channels. You look at one of your pixels, And then you go one step to the left, one step up, one step left and up, one step right and up, right. And you get the idea. One step below to the left, right below and below to the right. And these are these numbers, -101, -101 is one step to the left, right. Now, rather than having only one W, you're gonna end up with 9 Ws. So don't worry about these two, it's just to make the indices correct, because you want to have W11, W12, W13. You don't want to have W -1, -1. We are not comfortable working with negative numbers, so let's just add a 2. This is just gonna give you 9 matrices, and they're gonna be in this dimension. You're gonna look at 9 pixels at the input. Here you are looking at only 1 pixel at the input. Here you are looking at 9 pixels at the input. You change their dimension from RC, you're gonna go to RC prime, and then you sum. It's gonna give you a single vector for ijth pixel, which is C prime dimensional. But then you're gonna take that and slide it over your image to give you the rest of the pixels. Again, you are sharing parameters. When you visually speaking, I'm gonna tell you what is S. Visually speaking, this is what is happening. You take a window of 9 pixels, and then that's gonna give you a single pixel at the output. If you want to end up with all of these pixels, you need to slide this window over your image. S is the stride, which is telling you, yes, you're sliding, but are you taking one step to the right, or are you taking 2 steps to the right to shift the window? Or you shift the window 3 steps to the right. And that way, if your stride is bigger than 1, you're reducing the resolution. Your H and W are gonna reduce. They're gonna end up being H prime and W prime, which are less than H and W. So that's one way to reduce the resolution. And as I said, the convolution operation takes as input an image, and it's gonna output another image. And the output image that is coming out of this convolution operation is gonna be called feature maps. So you have a map of features and multiple maps of features. In this case, C prime maps of features. Okay, so far so good. But this is not what we want. We actually want a single vector. Convolution is getting close. It's giving us, it's taking as input an image and it's outputting another image. So it's taking an input as input a tensor, it's outputting another tensor. But in the end, you want to end up with a single vector. So you keep reducing the resolution. So I'm gonna answer your question after I finish the slides. Actually, this slide. Then I'm gonna answer questions. There is this idea of pooling and max pooling, which is very similar to what you are doing with convolution. You look at 1 pixel to the left, right, up, down. Rather than having some weights here getting multiplied by some vectors, you are just finding the maximum values. The difference between a 3x3 convolution and a 3x3 pooling is that you keep the dimension. You go from dimension C prime to dimension C prime. But with convolutions, you change that. You changed from dimension C to dimension C prime. That's max pooling. And these maximum operations, because Y is a vector, they're gonna be done element-wise. So it's element-wise maximization. Still, it doesn't solve our problem. Maybe if there's bigger than 1, you're reducing the resolution. It's gonna be H prime and W prime, less than H and W, but still it's not a vector. How do you get the vector out? And by the way, pooling is not introducing any new parameters. There is no weight and biases here. How do you get a vector representation out? You do global average pooling. So this maximum is gonna be average. This maximum is gonna be average. This interval is gonna be the entire image, not only the pixel to the left and right, but your entire input pixels. As you average them out, you're gonna end up with a single vector. And that's gonna solve your problem. I think visually speaking, what convolutions do is very similar to playing with a dough. You take an image, which is like this, you keep massaging it so that H and W become smaller and smaller. So you reduce the resolution. At the same time, you don't want to lose information. You keep increasing the C channel. You're gonna have more and more channels. So you keep massaging your dough until you end up with a vector. And the question is, how do you learn these parameters? Now that your data is in the form of vectors, you put a multi-layer perceptron on top of X. These are some additional parameters. You get a probability vector out. The rest of it is what we did last session. You write down your negative log of likelihood. That's going to give you a loss function, and you minimize it with respect to not only W, V, A, and B, but also these filters. And the filter size here is 3 by 3. I think now is a good time for me to stop and answer questions. For those of you who want to leave, you can leave. And for those of you who want to stay and ask questions, I'll be around. Okay, let's start with the last question first. How do we initialize the convolution matrix? How do you initialize W? This is exactly why I want you to keep watching these videos over the weekend. You start with ImageNet, then you learn about dropout, you learn about network-in-network, global average pooling, VGG, GoogleNet, and inception architectures, batch normalization. And here is where you're going to find your answer, Sabrina. How do you initialize your parameters properly? That depends on your activation function. That depends on the input size, the output size. So delving deep into rectifiers is going to answer your question. So I want you to watch up until slide 11 over the weekend. Now the question is, what are betas for MLP for this convolutional neural network architecture? Your betas are going to be a list of W, V, A, B. These are the parameters, and your weights and biases for the convolution. So the convolution has a bias also, which I'm removing. I'm not showing it here. And that's going to give you a list of your parameters that you're going to optimize over. Does that answer your question? And then what parameters are exactly being shared? That's a great question. Where is the sharing coming in? For each output pixel, you're using these 9 matrices. And these 9 matrices are independent of the output pixels. They don't depend on I and J. See, this W is only a function of your window, I prime and J prime. They don't depend on I and J. It means that for pixel 1 and 1, you're using 9 matrices. For pixel 1 and 2, you're using the same 9 matrices. Exactly. So the question is the choice of 3 by 3 convolution and therefore 9 matrices a hyperparameter? Of course. So that's going to be part of your alpha. That's going to be part of your hyperparameters. You need to first say, and this C prime is also a hyperparameter. Does that answer your question? Okay, go ahead. What's the question?
Could you go over why there's 9 matrices? I got the sense that you just pick W, the 3 by 3 convolution matrix, or whatever the dimension is at the beginning, and you just slide it around the original image. Where are you getting 9 matrices from?
You're getting 9 matrices because I started with 1 by 1 convolutions to give you the idea that you're going to end up with only 1 matrix. Okay, it's 1 times 1. 3 by 3 convolutions, you're going to end up with 9 matrices. You have more parameters. And why is that? Because you are looking at 9 input pixels. Because you have 9 input pixels, they are in dimension C, you want to change their dimensions. And each pixel in that window is going to have its own weight. And that's going to give you 9 matrices. Does that answer your question? So in the end, W is going to end up being a tensor. It's going to end up being 4-dimensional tensor. It's going to be in R3 by 3 by C prime by C. So the total number of parameters is 9 times bigger compared to 1 by 1. Does that answer your question?
Yeah, I think I just need to look at that a bit more. Thank you.
Yeah. So the question is, once we reduce the size, I guess you mean the resolution, where are we learning the features? So you're just writing a recipe when you take an image and in the end you turn it into a vector, you're just writing a recipe. You're saying that my weights and biases in the convolution are actually the way that I'm going to keep massaging my image. I'm going to reduce the resolution, increase the number of channels so that I'm not losing information. But now your question is, how do you actually come up with W? What is the best way to massage it into a vector? And that's the role of training. That's why you do training. You write down the loss function and you optimize over it. Does that answer your question? Can we talk about global average pooling? Yes. For global average pooling, it's very similar to the idea that we started with. How about doing an average over the entire set of pixels? And that's going to give you a vector that has a dimension c. But the idea is to wait up until you reduce the resolution enough. Wait until you increase the number of channels enough before you do that averaging. So you're just averaging, in the end, a very small h, maybe a 7x7 image that has a lot of channels. So you're averaging over the h and w. Does that answer your question? So it's just pulling over the entire resolution. Exactly. So this is pulling, global pulling, over the entire resolution, unlike what you were doing here, which is pulling over a window of 3x3. So yes. And there is another question in the chat. So we could rebuild the image from the vector representation if we know the W matrices. Most of these operations are not invertible because there is some nonlinearity also. When you take your image, you apply your convolution, then you're going to do ReLU. That's going to lose some information. But in principle, there should be a mapping taking you back from X to capital X without you losing much information. We cannot invert this right away, but you are not losing much information. You're just aggregating the information in your image. Yes, in principle, you are not losing much information. You should be able to go back. You're keeping the same amount of information, hopefully. There is no proof for that, but that's the intuition. Okay, perfect. Any other questions? Did I answer all of your questions? So for next session, make sure that you're watching up until slide 11. And the ones that don't have a video, I'm going to be covering in class. So don't worry about them. Okay, perfect. Okay, cool.